Thank you, organizers. Thank you, Winston. Thank you, Howard, for letting me talk at this really great symposium. I'm going to So as Winston pointed out, we're going to try to address some of the... You can turn that off. Oh, can I turn this off? I cannot balance it too much.
Is that talking to this one?
No, I want to talk to this one.
Oh, you want to talk?
Yes,
okay.
Because, yes. Hello? Yeah, sorry, I can't bend all the time to this microphone. It creates me a headache, so sorry about it. So there is absolutely no requirement for me to introduce 16S bioinformatics to this audience, and you've heard a lot of great things about it. And I'm going to focus very narrowly only on 16S because there is way too much to talk about 16S, and I have just very few minutes. So I'm going to actually rush through a lot of issues that we still have non-addressed. And we'll see actually how you guys agree or not from my perspective what are the problems are. So what are the challenges still left in this field? I mean, we've heard all these wonderful stories from the speakers before me, all these publications in Science, Nature coming out. So do we still have anything in the 16S field for sequencing that's still left for us to resolve? And actually, if you remember, try to remember our previous colleagues that presented, you would see that most of the data that was shown was maximally done on a genus level. There are very few people who push the limits, go to the species level. And I think that is important, and maybe we can discuss that further. So the other question is that how do we normalize the data? It's many people do different things. There is really no very good standard. And the least favorite problem is actually noise that comes from every single source possible. It's a technical noise, biological noise, and it goes from sequencing errors all the way down to the cross-run contaminations. For example, did you guys know that when you run your MySeq, a guy that runs the MySeq after you may have identified your sequence in his own run? So it's very important to rotate your barcodes. So this is kind of one of the solutions for that. Then we have the multiple hypothesis problem. And the multiple hypothesis problem becomes more and more critical as you go for bigger and bigger number of OTUs, or if you want to go for unique sequence analysis. And then the most important part, how would you design your experiment so it actually yields you exactly what you want to find? So we're not going to touch all these problems. Maybe other people will. But so is actually the species-level analysis possible at all? I would argue that probably it is, but is it necessary at all? So what is the problem with the species-level analysis? So we don't have good reference databases. So the best databases that we have, for example, the Silva, they're mostly designed for the genus level. The least favorite for people, like from Green Genes, they do have species level, but it's not really good. So we need a really good reference database. We ended up doing our own reference databases. So here we go. Then the biggest problem for what I can see in this field is actually finding the correct primers. And I'm going to dive into this in the next slide. But what happens is that amplification only a portion of the 16S would result in decreased diversity of your sample because you're sequencing just a small portion of it. So at the end, you don't have the full length of 16S to decipher what actually the species is. You just have 200 base pairs, maximum 450 for the MySeq. So that leads to so-called collapse of the multiple sequences in one. And on top of it, the primers do not amplify all the bacteria. So even though we call them pan-16S, actually they amplify maximum 95% of the bacteria. Some actually do a very bad job. The favorite primer for V1, V3 amplifies only 20% of bacteria. So, but what kind of benefits do we expect from this type of species-level analysis? It gives you a more granular view, and I would argue that it gives you a more accurate view of the gut microbiota. So, and on top of it, you may identify species that actually are more significant because the genus sometimes contains multiple species. So what is the guarantee that the species that drives the phenotype is not diluted by another species that in the same genus? So let's focus on the primer. This is an example of what will happen to your sequences once you use the most favorite primer set from Patchloss and Comparative. So you will collapse all of these sequences from actually different bacteria. This is a good example because some people were interested in this auditorium of Staphylococcus, and see epidermis and aureus becomes the same sequence. The same goes for E. coli. For E. coli, actually, things are much worse because now E. coli becomes absolutely identical with Shigella. So this is not what we want. So if we use Patrick Schloss primers, the one that everybody's here probably using, we cannot distinguish Shigella from E. coli. It's just impossible. So what can we do about it? So these are, for example, the combinations of different primers that I just ran for in silico PCR for demonstration. So these are 10 pairs. Some of them are favorite primers that we'll use. This is the Schloss primer. This is the Klockner primer and / Illumina that Illumina recommends for the SOP right now. And these are some other combinations. And these are the lengths of these PCR products. So I'm not going to bore you with this table. I'm just going to show this as a graph. So if we plot the proportion of unique sequences, meaning that after we collapse all of that and put them in a product of PCR length, we see that there is some sort of a correlation with the length of the PCR product. So the longer the product is, logically, you're going to end up with more unique sequences. You can see that in this table here. So the best primer, actually, that gives you the best outcome is the longest one, is the one that is about 1,000 base pairs long. The problem with these primers, actually, is that they do not amplify all of the bacteria. So some of them amplify 95%, as I said, some of them amplify 80%. And for your kind of demonstration purposes, the one that we use for V1, V3, very common primer, it amplifies only 20% of the bacterial sequences. However, it's a very good primer regarding speciation. So many people found out that actually this primer works really well for staph separations and streptococcus. And the reason is because it's all of the sequences that it produces are unique. So having this kind of graph allows us to demonstrate that probably the best primers for us to use, the one that we can sequence still long enough, are somewhere in this kind of area. So the information to take away that there are primers better than Schloss if you prefer complete overlap. So this primer, for example, combination gives us this with the same length as Schloss Caprese primer, gives us very high proportion of amplified sequences, and a lot of them are unique. So there are primers that are actually out there that might perform better than the one that we use already. So now switching gears again, because there are a lot of problems to discuss, and I want to discuss multiple comparison problem. which actually connected to some other problems as well. So I apologize for people who know this stuff really well, but I promise I'll be very quick. So we know when this throw of a coin problem. So if you throw a coin, and then if the coin lands up 9 times heads up and just 1 opposite way, the chance of that happening is 1%. But if you throw in at the same time 100 coins, it's actually almost guaranteed that it's going to happen, right? So that's why we use this Banferroni correction. That correction is the one that everybody hates, because what is happening, you have all these beautiful, significant results, but then when you apply this correction, everything poof and disappears. You know, so is it possible to deal with it? Is it completely, you know, end of your analysis? And if you think about it, why do we treat these all the bacteria or genes or whatever the same way? They're all different. So why would you take E. coli and say, I apply the same hypothesis for E. coli as lactobacillus? It doesn't make sense. They're all different. So they're all going to be behaving differently, have different dynamic range. So why do we use it? And I'm going to challenge you, why does it work? Because we do know that FDR correction works, or any other corrections. And the reason has to do with this kind of thing. I'm going to get back to the another slide, and you'll see why. So actually, continuing the coin analogy, if you're going to be flipping the coins, okay, and you know that it's exactly 50%, so your coin is absolutely balanced, you're going to end up flipping the coin, and let's say you did it 5 times. You have a very big confidence intervals, meaning that you do not really trust your data. So you have to flip coin a lot of times, 500 times, before you actually end up with something really reasonable. So to visualize this with microbiome data, what does it mean for us? So this is what I did for from the sequencing data. So I had about 10 million reads from one of the sequencing runs. And I just subsampled it 10 times. So the same pool that I just randomly took 100,000 sequences from. So I just generated this kind of mock data, and I plotted this against the actual data. So you can see pretty nicely that you have a lot of variability in the very beginning, which actually then subsides. And if you plot this as a variance is simply standard deviation divided by mean. And if you plot the variance against the number of the unique sequences, you're going to see that the variance drops pretty nicely to very low, extremely low levels if you have very large number of your sample size. So what does it tell you, all this data? That means that if you don't have this piece of the data, you're going to have pretty clean data. To put it another way, the bacteria or whatever reads or genes or anything that you're working with that represent the same coin that you keep flipping are these ones, because this is noise, and noise is identical everywhere. So this is the stuff that I propose to you guys to delete it from your data sets. So we don't need any kind of rare reads. They provide you absolutely no purposes, so just get rid of them. The question would be, what would be your cutoff? And that is up to you. I mean, we can go do some math, but it's really up to your sample size, because if you have a very large sample size, then you can afford yourself to keep more rare reads. If you don't, then if you have very few samples, then you have to be very generous. You know, if you want rare reads, just do deeper sequencing. And by doing this, you're actually doing yourself a double favor, because this is more community sequenced, which without any kind of filtering, and these are mismatches because we know what the mock community is composed of, we know what kind of sequences it contains, and we can see that mock community contains very few sequences, only like 20 or something. So, and here they are. And the rest is just noise. So these are our accurate sequences. And if we would have applied a filter, which is basically just a cut of about 100, we would have get rid of all of these problems, which include, by the way, also chimeras. Because chimeras, as it turned out, that happens, everybody knows here about the chimeras, I hope. So they're not that abundant. So they usually end up towards the end of your PCR. So by doing some sort of a cutoff, you can remove them as well. So the other benefit from cutting your rare reads out is in the possibility for you now to do sequence-based analysis instead of using OTUs. So I actually, in general, kind of against OTUs for very obvious reasons, because OTU, even though it's a bit artificial, even some people would argue it's the most logical, it's better than species level something. But in one hand, it may be that. In other hands, it may be this. And on top of it, one OTU can contain several species. So by analyzing unique sequences, you may end up actually doing yourself a favor and working with real non-imputed data. And this demonstrates that it actually works. So this is just some data set that we can put on a PCA. This is not Unifrag, it's just a regular PCA. And you can see that the groups are very nicely separated, and the heat map demonstrates very nice differences between the different groups. So, and this is done again just based on sequences, not on OTUs. So, because now you cut them pretty dramatically, you can use your sequences. So, okay, so now you have done all of your clearing, you sorted out all kind of your problems with your quality of your reads, etc., and you got to the point that you need to identify some differences. So between your samples or figure out what's going on with your phenomenon. And so what are the rules how to approach the analysis? And the rules are pretty simple. So your experiment has to be designed first. Like way before you approach any kind of sequencing, it has to be very carefully designed. And to my opinion, maybe other people here would not agree, the design has to have very limited number of goals, preferably 1, maximum 2. Then your experiment has to be designed with idea how to eliminate the noise, because noise is actually #1 enemy for any type of analysis. Experimental design also should contain strategy to identify your candidates. It can be as complex as you want. However, you should keep in mind that by increasing the complexity, you're going to increase the type 2 error. So you're going to generate a lot of false negatives. And most importantly, your experiment has to have some sort of way to be validated, whatever that is. And this is one of the examples of such kind of design. So we had a question that we needed to address: which bacteria are responsible for higher levels of TNF in a tumor. So what we found is that if we use several perturbation approaches and then combine them together, we could identify potential candidates. And this is what we did. We had 3 perturbation approaches in which we correlated the bacteria frequencies with the abundance of TNF in a tumor. And in the intersection, there were only a few candidates. And one of these candidates turned out to be Elastipis shahi. So we took that bacteria, colonized the antibiotic-treated mice. So we had the phenomenon where antibiotic-treated mice had reduced production of TNF. And here we have seen that these bacteria specifically restored level of the TNF to higher levels. So This is just kind of one way to demonstrate that this approach can work. Then how do we deal with the variability within your experimental samples? Because variability is it's a huge, huge problem, at least in our work. Personally, I can tell you from which cage this mouse came from. It's like a fingerprinting, and people say that criminal justice now going to be using the personal microbiome to track us. So it's very, very variable and very personal to whatever. So what we saw is that individual housing of animals actually works pretty well. So in this particular project, this was initial mice. The size, it's at different days. So we could see that if you, even if when you mix the all the data together, you can see that the before treatment, they all occupied the red and blue, the same space, and then they moved to different places. And the good thing about this is that I can trust this data because these mice were housed separately. So this is just for your personal comfort that you can trust this data. For mouse experiments that not many people in this audience maybe are doing, is that we co-house them for our experimental purposes. And we can see that the co-housing actually changes the microbiota of these red circles, so they move towards the blue. So, and then you can work with them. And finally, I just want to bring to your attention something that everybody's here using is the dimensional reduction. So everybody's using here PCA maps. But I wonder how many people of you use PCA accesses beyond 3, because the PCA analysis generates a lot of access. It just reduces the dimensions from hundreds to less. And I'm not quite sure which of these axes is correct. So you actually have to do some analysis to demonstrate that PCA1 or PCA2 is more important. So and this is one of the examples of such analysis. This is just traditional PCA. And then there is this tool, it's called TSNA, where you do not need to reduce to multiple dimensions like in principal component analysis. You can just reduce them to 2. So you can squeeze all the information that you have in your data set and somehow put them on 2D map. So let's say if your difference between patients between colitis and non-colitis, they were hiding in dimension 4 or 5, and you missed them when you did your PCA visualization. Using the TSNA, most likely you're going to see it. So, and these are some conclusions that if you guys are going to go for species-level analysis, it's best to revalidate your primers. The reducing noise by just trimming your low abundance reads is going to be very good for you. And the careful design of experiment for 16S is critical for successful identification of bacteria of interest. So with that, I want to thank Giorgio Trinchieri for support of our group and microbiome efforts, Jonathan Badger here for useful discussions. Thank you very much.
Thank you, Amiran.